We use the word work in our everyday language to refer to some form of exertion. It may be physical or mental, or at times for various activities, such as a farmer plowing the field, a construction worker carrying bricks, a student studying for a competitive examination, an artist painting a beautiful landscape. All are said to be working. But in physics, the word work covers a definite and precise meaning. In today's video, we are going to discuss how physics defines the term work. So, without wasting any time, let's start. Somebody who has the capacity to work for 14 to 16 hours a day is said to have a large stamina or energy. We admire a long-distance runner for her stamina or energy. Thus, energy is our capacity to do work. In physics too, the term energy is related to work in this sense, but as we said, the term work itself is defined much more precisely. In physics, the term work is used in relation to the displacement produced by the force. The work is said to be done only when a body moves under the influence of a force. If there is no motion produced in the body, even when a force acts on it, the work done is said to be zero. So, work is said to be done only when the force applied on a body makes the body move, that is, there is a displacement of the body. Let's understand with an example. Consider a constant force F acting on an object of mass m. The object undergoes a displacement d in the positive x direction as shown. The formula for the work done by the force W is equal to F into d. Now, we see that if there is no displacement, there is no work done, even if the force is large. Thus, when you push hard against a rigid brick wall, the force you exert on the wall does no work. Yet your muscles are alternatively contracting and relaxing, and internal energy is being used up, and you do get tired. Thus, the meaning of work in physics is different from its usage in everyday language. It is not always necessary that the force causes displacement of the body in the direction of force. If under some circumstances, a force produces displacement in the body in a direction other than the direction of force, then to determine the amount of work done by the force, we have to find the component of displacement of the body in the direction of force. So, let us consider a constant force F acts on a body along AB, and it displaces the body on an inclined surface such that the point of application of the force moves from A to C. The displacement of the body AC is equal to small d, which is at an angle theta to the direction of force. In order to calculate the work done by the force F, we have to find the component of the displacement in the direction of force for which a perpendicular CB is drawn from C on AB. Then the component of displacement in the direction of force is equal to AB. Hence, work done W is equal to F into AB. But in the right angle triangle ABC, cos theta is equal to base by hypotenuse or AB by AC. Since AC is equal to small d, AB is equal to d cos theta. Hence, W is equal to F into d cos theta. This is the expression of work due to a constant force, where the direction of the applied force makes an angle of theta with the direction of the displacement. Case number 1. If the displacement is in the direction of force, that is, theta is equal to 0 degrees, then cos 0 degrees equals 1. Therefore, W is equal to F into d. Here, the work done is maximum and positive. Example. In free fall of a body of mass m under gravity through a height h from A to B, the force of gravity, F equals mg, is in the direction of displacement, and the work done by the force of gravity is W equals F into d, or mgh. Case number 2. If the displacement is normal to the direction of force, that is, theta is equal to 90 degrees, then cos 90 degrees equals 0. Therefore, W is equal to 0. Hence, the work done is 0. Example. When a coolie, carrying some load on his head, moves, no work is done against the force of gravity, because the displacement of load being horizontal is normal to the direction of the force of gravity. Although Cooley does work against the force of friction when he moves with it. Conditions for the work done by a force to be zero. From these discussions, it is very clear that the amount of work done by a force is zero in the following two situations. Number 1. When there is no displacement, that is d equals 0. And number 2. When the displacement is normal to the direction of the force, that is theta is equal to 90 degrees. Case number 3. If the displacement is in a direction opposite to the force, theta is equal to 180 degrees, then cos 180 degrees equals minus 1. Therefore, W is equal to minus F into d. Here, the work done is negative. This is usually the case when the force opposes the motion or it tries to stop a moving body. For example, when a body moves on a surface, the force of friction between the body and the surface is in the direction opposite to the motion of the body, and so the work done by the force of friction is negative. The expression for work we saw earlier is only for constant forces. But a constant force is rare. It is the variable force, which we usually encounter most of the time. So, let's take a look at the expression for the work done by a variable force. The curved line in the graph shows a varying force in one dimension. Now, if the displacement del x is small, we can take the force Fx as approximately constant, and the work done is then del W is equal to Fx del x. Adding these successive rectangular areas in the picture, we get the total work done as W is nearly equal to summation xi to xf Fx del x, where the summation is from the initial position xi to the final position xf. If the displacements are allowed to approach zero, then the number of terms in the sum increases without limit, but the sum approaches a definite value equal to the area under the curve. Then the work done, W is equal to limit del x tends to 0, summation xi to xf Fx del x, or integration xi to xf Fx dx, where limit stands for the limit of the sum when del x tends to 0. Thus, for a varying force, the work done can be expressed as a definite integral of force over displacement. This is the expression of the work done by a variable force. The SI unit of work is joule. Since work is equal to force into displacement, therefore 1 joule is equal to 1 Newton into 1 meter. Thus, 1 joule of work is said to be done when a force of 1 Newton displaces a body through a distance of 1 meter in its own direction. The CGS unit of work is erg. Since work is equal to force into displacement, therefore 1 erg is equal to 1 dyne into 1 centimeter. Thus, 1 erg of work is said to be done when a force of 1 dyne displaces a body through a distance of 1 centimeter in its own direction. The dimension of work is equal to the dimension of force into the dimension of displacement. The dimension of force is mLt minus 2, and the dimension of displacement is L. Thus, the dimension of work is equal to mL2t minus 2. If you enjoyed this video, then don't forget to like, share, and comments on it. To watch more such videos, also subscribe to this channel. So that's all for today. See you in the next video.